Good afternoon, everyone. I'm happy to introduce Bruno Sterner, who's a postdoc here in our department and works on isogeny-based cryptography with David Zhao. So before coming here, Bruno was a postdoc at INRIA Saclay, working with Benjamin Smith, and before that was a PhD student at the University of Surrey, working with Robert Granger. The floor is yours.
Thanks, Sam. Thanks for the introduction, and thanks everyone for coming. I think I've tried my best to make myself acquainted to everyone, but if I haven't, nice to meet you. I'm going to be talking about some recent work that I've done in collaboration with a couple of Dutch guys, Eric and Wessel. And in this work, we're interested in finding certain types of consecutive integers. In particular, we're interested in finding these ones in purple in comparison to all these others that are in gray. Now, I'm in a room full of smart people doing lots of different types of research, from combinatorics to optimization, and maybe there's some interesting reasons why these integers are interesting in the context of your work. But one very, very natural reason why you might be interested in these integers is when you look at their factorization. Now, for integers of this size, what should you expect from their factorization? Well, you should expect, on average, that there should be a large prime factor. You see that in the first integer, the one that ends in 7,1, has a really, really large prime factor. The next ones have large prime factors, not as large, but they're still notably large. Some of these have small prime factors, just because these prime factors occur more frequently than others. Like you can see, a lot of them have 2 as a divisor because they're even. Nothing too surprising there. But all of them in gray have some sort of a large prime factor. These integers in purple are the exception to this rule, where the largest prime factor is really, really small, which we call smooth integers. And it's even more rare that you get smooth integers that are consecutive, like this. And we call such a pair of consecutive smooth integers a smooth twin. You might be wondering, okay, these integers are cool, but why did they come across in isogeny-based research? Why did I even come across this sort of computational number theoretic problem in my research? Well, the problem that I came around to was there were certain cryptosystems that were instantiated on a large prime P of cryptographic size. And when I say cryptographic size, just think of it being roughly 256 bits, for which P squared minus 1 is either entirely smooth, the largest prime factor in P squared minus 1 is very small, or there is some large divisor of P squared minus 1, which is smooth. Maybe the rest of it is not smooth, but that doesn't matter too much. This was originally proposed in the context of B-side, which was an adaptation of SIDH. It's been proposed also in SkiSign, the first version of SkiSign. And then more recently, there's some new encryption schemes, Poke and its many variants that can have benefits from these sort of parameters. And the idea in using this in isogeny-based cryptography is that you're working with elliptic curves whose number of points is p minus 1 and p plus 1 all squared. And you can kind of transport these between the two by doing like some quadratic twist operation. And you can do efficient isogeny computations because p squared minus 1 is smooth. So that's like the cryptographic relevance for why these primes are interesting. For the most part, you can kind of forget about this because really our goal is to find these primes, or more precisely, find these smooth twins. And you might think, okay, these smooth twins, this seems slightly different from this problem, right? I've introduced this prime, where does that come across in the smooth twin? Instead of the consecutive integers being smooth, I've got this p squared minus 1. It seems very, very different. I mean, sort of the same, but at the same time also quite different. But actually, these are more or less the same. If you have a smooth twin, and you take their sum, you add r and r plus 1 to get 2r plus 1. If this is prime, then you get something suitable for isogeny-based cryptography. P squared minus 1 factors entirely in r and r plus 1 up to this factor of 4. And like ensuring primality, this is not too tricky. You know, by the prime number theorem, that if you have enough of these sort of primes, you can expect one of them to be prime, so that's not the difficult part. The really difficult part is finding these smooth twins. So we're going to focus in this talk on like finding better algorithms to find these smooth twins. I want to remark that in isogeny-based cryptography, you don't necessarily need all of it to be smooth. A large enough smooth factor is sufficient. For instance, this parameter here at the bottom was one that was proposed for this submission of ski sign. And you can see here that all the factors that are in brown, or I'm not sure how this color is coming out, but let's say it's brown. All these factors in brown are the smooth factors, and this is what you use in your applications. I said like I'm going to focus on the fully smooth setting, but as a consequence of our work, we were able to find a new parameter which has a much, much smaller smoothness bound on the smooth part of p² minus 1. In particular, it decreased from something that was about 2,000 to now being something that's like 500. This is a nice benefit from the cryptographic point of view because signing can be faster and things like this. But yeah, again, I'm going to focus on this fully smooth twin setting. So let's formalize things a little bit and properly notate smooth twins with a smoothness bound B. And I particularly call a pair of consecutive integers a B-smooth twin if their product R and R+1 is B-smooth. The fact that their product is smooth is the same as the integers themselves being smooth, so we can make this distinction. Here are a couple more smooth twins to go along the first twin that I mentioned in my first slide. And these are actually my favorite smooth twins. A bit weird for me to say this, but I'm a bit of a weird guy. The first one, the reason why it's interesting is it comes across as an oddity in a different algorithm that I just like always remember, and then whenever I speak about it with people outside the research field, they always want to give me an example, and I always give them this one because it's small and I always seem to remember it. The second one is more interesting for the masses, and it might not be obvious why this is one of my favorite smooth twins, but hopefully if you see this, then maybe it's a bit clearer that it's quite interesting why this one here is my favorite in terms of the factorizations of these things. What might be slightly surprising to you is that if you fix a smoothness bound B and you want to consider all B-smooth twins, this whole set is finite. And you can really explicitly count how many B-smooth twins there are. For instance, for this B equals 7, the pointer is a bit faint, but for the B equals 7, there are 23 smooth twins. And this example on this 4374 example is the largest B-smooth twin among these 27. This other example that's 23 smooth, this is not the largest, but it's the second largest, but whatever. It's cool enough as it is, so it's nice to show. I will use some notation to refer to the largest B-smooth twin, and I will refer to this as optimal smooth twins. I might interject between the two, and that's my apologies if I do this. I will typically refer to the optimal one if it's the largest that we know, and the largest, and just say it's the largest if it's the largest one that we have in our disposal, but we don't think it's the largest. We think we can find a larger one. And prior to this work, there wasn't really an idea of how this grows. We got a vague sense because we know how how the sets kind of just grow, but we didn't necessarily have anything concrete. And this is something that we'll come back to. We need this later on. And actually, as part of this work, I want to just remark that we proved a small little result that tells you the asymptotic growth of B-smooth twins. In particular, the optimal one grows as some exponential e to the power 2e times square root b. Just have this in the back of your mind. It's not too important for now, but it's nice to just keep in there. So how do you find these optimal twins? And in the literature, there's only really one way of doing this, and that's through solving Pell equations. And just for some notation, this is going to be consistent throughout the talk. I'm going to refer to PB to be all the primes up to B, and as usual, pi of B to be the cardinality of this set. And the observation that you can make is that you can see smooth twins as a solution to a Pell equation. And maybe I can use the blackboard to be explicit about this. If you have a smooth twin of this form, and you do something similar to like what we did in the isogeny-based discussion, and you take their sum, and again, you do the x squared minus 1, which is what I wrote down before, and we saw that this was something like this. Since this is a smooth twin, then this is also smooth, and we can decompose this into its, let's include the 4 out front, into its square-free parts and its square parts when we divide through by 4. And you can see here that if we just manipulate things ever so slightly, we get a Pell equation. And vice versa, you can solve these Pell equations to get back your smooth twins. And in particular, there are a lot of Pell equations you have to solve. You have to solve on the order of 2 to the pi b Pell equations to find categorically all B smooth twins. And that's how the numbers that I presented on the previous slides, that's where those numbers come from. They come from solving all of these Pell equations and then actually figuring out how many there are. So for instance, for b equals 7, there's all of these 15 Pell equations that you have to solve. And this number grows, but b equals 7 is not the largest that's been done. It's been b equals 40, which was done by Lehmer, which was like, he was the first person that characterized smooth twins in this way. And then more recently, Luca Nyman has done for b equals 100, and then more recently, in view of these cryptographic applications coming from isogenies, Costello did this for b equals 113. In some sense, this has gone a little bit overboard for what we want, right? We were really wanting to find the optimal B-smooth twin, and instead, we've really gone ahead and found them all. So it's kind of a bit too much, and you might ask, can we really be selective about how we do this in order to just find the optimal one? And the answer really is no. You don't really know which Pell equation the optimal one or one of the largest ones is going to come from. I think off the top of my head, the Pell equation with d equals 42, this one over here, is the Pell equation that results into that, my favorite 7 smooth twin that I mentioned on the previous slide. But that's also me not maybe remembering it correctly, so if it might be one of the neighbors, I can't really tell you. So like pinpointing down the largest one, the optimal one, is really quite tricky for this without completely exhaustively solving all Pell equations. And that's where we come in. We have a new characterization of smooth twins, which allows you to, with one instantiation, really find the optimal one. And the idea is based on lattices. And the characterization, which I'll talk about a lot throughout the rest of this talk, is that we'll see smooth twins as short vectors in some sort of lattice, which is the prime number lattice. And in particular, the shortest vectors in this lattice are pairs of integers that are smooth and differ by something small. This includes the smooth twins. With the parameters of this lattice, as I said, we can really go ahead and find these short vectors to find these optimal B-smooth twins. And for instance, this 157 bits B-smooth twin was found with our approach. This is not the largest one that we find. We do find some larger ones, including this one, which is no longer guaranteed to be optimal. Basically coming from the fact of that theorem that I said before. That theorem gives us a guide of how the B-smooth twin grows, and this falls slightly short of that, whereas this one goes above that. So we have confidence that this one is the optimal one, but less so with the other ones. And these are not the largest ones that we find. I don't want to spoil it just yet, but we do find some larger twins in both cases. So I've hinted that we're going to do some stuff with lattices, so let's just get some preliminaries down. Maybe you all are familiar with lattices or have come across them, but it's good to set some notation down. A lattice is, as we all know, a discrete subgroup of Euclidean space, and I'm really emphasizing that we're going to be working purely in the Euclidean norm. You could do all of this in a different norm, but just for practicality reasons, it's easier to just work with the Euclidean one. This is a bit of an abstract definition of lattices, and more concretely, you can define it in terms of a basis. You have some collection B1 up to Bn that's linear independent and spans the whole set, the whole lattice, or generates the whole lattice. And you can rewrite this in terms of a matrix and then multiply it by some vector x. And I'll refer to both the little b1 up to bn and the capital B as bases of the lattice. I've indicated that we should find short vectors in this lattice, so what are they? These are non-zero vectors in the lattice that have a small Euclidean norm. And in particular, you can formulate the shortest vector of the problem, which is to find the shortest vector that's non-zero in the lattice. For those that are familiar with lattice-based cryptography, this is really like the pure foundation of lattice-based cryptography, and you would want to construct lattice-based cryptosystems that reduce down to solving the shortest vector problem. Common notation for the shortest vector in the lattice, which is also referred to as the first minima, is this lambda 1 of L, is the norm of the shortest vector in the lattice. And it might be a little bit surprising, but computing this first minima and computing the shortest vector problem, actually finding the vector with the shortest norm, are basically the same thing. It's as hard to compute the first minima of the lattice as it is to find the vector that gives you the shortest vector in the lattice. But we can get an average idea of how the shortest vector, the norm of the shortest vector looks like, because there's this Gaussian heuristic which says that on average, this first minima is approximately this Gaussian heuristic GH of L, which is given by this expression. And more precisely, you can also quantify how many vectors there are in the lattice of a prescribed norm. And based on this Gaussian heuristic, it's roughly lambda over this Gaussian heuristic raised to the power of the dimension of the lattice n. So we have these short vectors, but how do we actually go ahead and find them? And then how do we actually go ahead and find them? Because there's like a whole collection of algorithms that we could use in practice. There's LLL over here on the left side, and then there's enumeration all the way on the right side. And all of these algorithms, okay, apart from two, they cover different sorts of short vectors. These two on the left side, they are lattice reduction algorithms, which reduces the basis of the lattice to something short, but not super, super short. BKZ is like a trade-off between the LLL and the algorithms on the right, where you can have the trade-off in the middle. Whereas the algorithms on the right really do find the shortest vectors in the lattice. And the more practical of these two is sieving. And I want to give a brief overview of how a sieving works. And this picture is really not to scale. You should really imagine this in many dimensions, where this has a bit more meaning. But yeah, I can only do 2 dimensions on this slide, so this is fine for now. The idea in lattice sieving is we're going to sample a whole bunch of vectors. All these vectors are in blue. Sample them at random. And especially if we're working in large dimension, they're not going to be short. They're going to be something non-trivially large in terms of their norm. Then for each pair of vectors, let's say these two on the bottom left, we're going to consider the vector that connects them, which amounts to just taking their difference. If this new vector is shorter than all of the other vectors that are in blue, we're going to include that in a new list. And I'm going to label this as an orange point. And I've just shifted it so that it's on par with the origin that's in red. We're going to do this for all pairs of vectors. And let's say we get this collection of orange vectors from all of this stuff. Then we're going to do the same thing again, but with these orange vectors. Consider each pair take their difference and see whether it gives you a shorter vector than what you had before. And you might see visually from this diagram that this vector you'll get from considering these two. And that would be a solution to your shortest vector problem. So a little bit more concretely, lattice sieving is an iterative thing whereby you have a large list of non-zero vectors that's kind of saturated by some upper bound radius, let's call it Ri. And then you're going to construct a new list of vectors by forming their difference and only keep the ones that give you a shorter vector compared to before. This choice of n doesn't really matter too much, but essentially it preserves the same amount of vectors in the new list. So if you start with n vectors of this number, then the number of vectors in the new list is also going to be about n. And so on and so on. And you keep repeating this until you've saturated all the shortest vectors in the lattice. And in particular, you will get not only the shortest vector, but all n shortest vectors in the lattice, which is cool. There's more sophisticated techniques that we can incorporate into this like naive strategy. For instance, instead of comparing every single pair of vectors, you only compare the vectors that are relatively close together. There's no point comparing two vectors that are on the opposite ends of your lattice. So you can group these vectors into buckets in some sense like this, and then there's an optimal way of doing this based on coding theory, which is beyond the scope of this, but it's quite cool to just say. The runtime and memory of all of these like advanced techniques of improving this lattice sieving, and if you throw all the heuristics that you want at all of this, is the following. The runtime is exponential, and the memory is also exponential in the lattice dimension. Which is not ideal for us if we want to use this later on, but it's good enough for what we'll see. But this is also the foundation for lattice-based crypto. All of this is implemented in this general Civ kernel, Jessica as well, and we use this in our implementation later on. So let's actually talk about the prime number lattice. This is what we wanted to use to find these smooth twins. And again, for a little bit more notation, I'm going to refer to a factor base to be a subset of primes up to b, subsets of pb, and this n to denote the number of primes in this factor base. And then we have some extra factors, scaling and weight factors, which are going to appear in the lattice itself. So the prime number lattice is this lattice with the following basis. The basis whereby on the top row, you have alpha, the scaling factor alpha multiplied by all of the log primes in your factor base. And then everything below it is just a diagonal matrix, alpha 1 across all the way up to alpha n. If this lattice looks familiar to you, you're not the only one that's considered it, because it's appeared all the way back in the 90s, whereby Schnorr and Adelman and other people considered using this lattice to factor integers and solve discrete logarithms. Unfortunately, in that context, it didn't really compete as an algorithm compared to other algorithms, let's say number field sieve or ECM or other things like this. But it's a cool thing to just like have as an arsenal that you could, in theory, factor and solve discrete logs, and eventually find smooth twins. So what the lattice vectors look like in this lattice, and we can just like compute a lattice vector, take a vector x, x1 up to xn, and multiply it by our basis matrix B. On the top, we have this big sum of alpha x1 log p1 all the way up to alpha xn log pn, and everything below is just an identity matrix. Up to some scalings, but whatever, and then you just multiply them across to get alpha 1, x1, all the way up to alpha n, xn. The top one, we can combine this into one big log. because of log laws and lots of stuff like this. And you get this rational A over B, which concretely is formed as follows. And it's really a division because some of these xi's could be negative, and that induces a division when you group it together. You can go the other way around. If you have a smooth rational like this, you just compute the exponent by symbolically just writing it like this. And then from that, you can get a lattice vector in the lattice. So this gives us like a correspondence between smooth rationals that are p-smooth, in the sense that like each A and B are only divisible by primes in P, and vectors in this lattice. This is really a one-to-one correspondence, and this is true for any alpha and alpha I that you choose, any factors. Now, we want to see what short vectors in this lattice are. So what are they? And the first point of call you might think is to actually symbolically write down what the norm is of this of such a lattice vector. And you can see here that symbolically we can just write it like this. And it's composed of two parts. We have this log, alpha log term, and this alpha I and xi term over here. And if you ask yourself, okay, which is the most important part in this formula, you might think that this term over here is the most important. Because if this A over B is approximately 1, or something really, really close to 1, then this is basically just going to be 0. So for such rationals A over B that's about 1, you're going to have a much smaller norm of a vector compared to other rationals and other vectors that, for which A over B is not 1, let's say if it's 2 or something larger. Let's see this visually with a few examples, just to kind of see this in practice. Let's see it's for small alpha. And I'm going to fix a lattice with the weights being alpha, log pi and the factor base being all primes up to 7. And I'm going to change alpha a few times and see what the shortest vectors are in this lattice. For alpha is 2 to the 8, 256. These here are the shortest vectors in this lattice. And you can see that the vectors correspond to rationals for which the numerator and denominator differ by 1. Not always the case. You have this example here where they differ by 2, but most of the time they differ by 1. And one observation that's good to have for now is that the size of the A and B in the shortest example, this 224 and 225, is roughly speaking the same as this choice of alpha that we made at the start, 256. And also this example where the difference was 2, this is slightly bigger than these examples, at least the numerator and denominator are, because this difference is slightly bigger. Good things to have in mind for now. Let's do the same thing, but with a slightly larger alpha. This time alpha is 2 to the 13, 1892. You can see here now that the shortest vectors in the lattice also correspond to smooth twins. So there's 2 examples here. But after that, they really don't correspond to smooth twins anymore. And in some sense, if we increase alpha, we can't expect to find many short vectors that correspond to smooth twins in this way. Let's do one more alpha for this lattice, which is slightly larger. Now this time, alpha is 2 to the 18, and now you can really see that none of the shortest vectors in this lattice correspond to smooth twins. The difference between the numerators and denominators is much, much larger than 1. But it's not like these smooth twins are not in this lattice anymore, because I mentioned that there's this correspondence between lattice vectors and smooth rationals. So these smooth twins should appear in this lattice. But the difference is because we've chosen a much larger alpha, it's no longer short anymore. The contribution of that alpha in the log term makes it non-zero anymore, and it makes it blows up. One more example before I continue further. Let's consider the same lattice that we had before with the same alpha. It was 2 to the 18, but we've increased our factor base. Instead of it just being all the primes up to 7, we now have all the primes up to 19. And let's see what the shortest vectors are in the lattice. You can see here now that the shortest vectors do correspond to smooth twins now. that sort of makes sense because as we increase the factor base, we should expect to find larger and larger smooth twins. So if we increase alpha in such a way, along with the factor base size, we should be able to find smooth twins. So we've seen in all of these examples that the shortest vectors, or the short vectors, really correspond to rationals that are really closely approximated to 1. And they are contributing into this term in the norm expression, which by the log laws, and this is being approximately 1, we can write it like this. And what we saw in all of these examples that the shortest vectors correspond to a choice of alpha that's roughly this, whereby, i.e. when we have smooth twins as the shortest vectors, this difference is just 1, and we just have alpha being approximately equal to r. And you saw that with the other examples when we had a shortest vector that corresponded to smooth rationals with a much, much larger difference, the b or the a that we have in the expression for alpha is much, much larger than alpha itself. But even this is not quite precise enough because, as I said, it was all the alphas in the examples was a bit larger than r. It wasn't just like alpha is a really good approximation of r. It was just like alpha is a little bit bigger than r. And actually, if you do the optimization of finding what is the best alpha that gives you the shortest vector for this smooth twin or this smooth rational, then we get this expression over here. And you can see here that we still have this b over a minus b in the bottom, basically r for smooth twins, but it's being multiplied by some small factor, whereby this beta 2 is the sum of xi's alpha i's. So if you choose this specific alpha, then you'll get a vector that's for which this particular smooth rational is the minimal vector in that lattice, let's say. But there's a problem with this, which is that, okay, you might think, okay, to compute this alpha, I should know what the smooth twin is because I'm using the xi's to compute this beta 2. And same here, I know what this b is, so surely you need to use this to compute this alpha. Well, it turns out that we don't have to be super, super precise. As I mentioned in the examples, I only really picked a power of 2. I didn't have to be super precise in terms of what that power was. I just picked it to be an integer power of 2. So we can just approximate it ever so slightly, and it doesn't really change the norm or this ratio too much. But you still want it to be a little bit bigger than the target size that you would want to find these smooth twins. So that more or less wraps up the discussion on these short vectors, but there's still one more thing which is choosing these alpha i's. And there's a whole bunch of different choices, so I don't think I'm going to have time to discuss all of these details too much, but there's a whole bunch of different choices. And the short vectors that you get from these different choices kind of correlate to the factorization structures of the smooth twins. I won't talk about it too much. But what I will say is we are able to prove under some heuristics that with this optimal alpha that I mentioned on the previous slide, where's the marker? Anyway, the alpha opt that we have over there, and the log pi choice for the weights, then optimal smooth twins, the largest B smooth twin in the lattice, is particularly short, or even sometimes the shortest vector in the lattice. So we can really use SVP to find these smooth twins. We weren't able to properly prove this sort of result for other alpha i's, but we experimentally showed this for some other ones. All of this was discussion for optimal smooth twins, but what about the smaller ones? And it turns out that, okay, you can't expect them all to arise from a shortest vector in the lattice for 2 reasons. The first one, which is kind of very obvious, which is that there are much more smaller twins than there are larger twins. So you can't expect them all to be the shortest vector or among the shortest vector in the lattice. More precisely, you could have some unusual prime powers in the factorization, giving a much larger contribution of this term in the norm expression. And this would be unusually large because, let's say if this prime is large and this xi is also large, then this is really going to be a lot larger than what you would normally have. One very obvious example is this smooth twin, for which r plus 1 clearly has a factor 107 to the power 6. So let's pop everything together and discuss actually finding these smooth twins. So the simple strategy is as follows. We set up some parameters of our lattice. We choose a scaling factor alpha, some weights alpha I, and we work in the full lattice that consists of all primes up to b, a factor base that consists of that. We're going to apply lattice sieving in this lattice to get a whole bunch of short vectors. We'll notate that with L short. For each short vector in this lattice, we're going to use that correspondence to compute what the corresponding A and B are in the smooth rational and return out all the pairs that differ by 1. Again, if you want to tailor things to find the optimal one, you might remember at the start that we proved this asymptotic on how optimal twins grow. And you want to basically choose alpha from this. Not this precisely, because this is really telling you the asymptotic, but you can do some numerical approximation of this results to concretely pinpoint down what you expect the largest B-smooth twin is. A small remark, which I think I'm going to very gloss over, which is that lattice sieving is very similar to another algorithm that's referred to CHM. But yeah, I think I'll skip that. So let's actually find these optimal B-smooth twins. And as I said before, this has only been done for B less than 113 in the literature. And the largest one is this one, for which the largest prime factor is 103, but yeah, sure. If you remember, this required solving a whole bunch of Pell equations at a computational cost that's 2 to the power of pi over b, because that's how many Pell equations you have to solve. And then there's a little extra term because you have to actually solve each Pell equation. So let's find these optimal smooth twins from our sieving-based approach. For instance, you can find this example above by choosing alpha is 2 to the 76, and you'll easily find this one. And okay, I chose this kind of arbitrarily, only for it to be slightly bigger than this. You can compute what the optimal one would be, and you can see it's only slightly bigger than this. So this guess was fairly good enough to find that smooth twin. So let's go beyond this and find larger optimal twins. For b equals 200 and choosing a scaling factor alpha is 2 to the 97, we find this smooth twin that I mentioned at the start. And you find it very easily, which is very, very cool. And to compare with the Pell equation approach, the computational cost really just boils down to solving one SVP in a prime number lattice. And the complexity of this, if you remember from one of the previous slides, was this 2 to the 0.292 pi of b referring to the dimension of the lattice, and then plus some error term. So there's a much smaller saving coming from just doing this one SVP solve. And so this allows us to go further and find larger optimal twins. This includes b equals 500, the example that I mentioned in my high-level slide, for which the factorization is this, as well as this larger one with b equals 517, which is the largest B-smooth twin for which we believe is optimal, which is very cool, I think. And yeah, as I mentioned before, we believe these are optimal in comparison to this optimal asymptotic that I mentioned before. I also mentioned earlier that we've found larger twins. These are no longer guaranteed to be optimal. And there are a couple of tricks that you can play with to find these larger ones. The first one is to use a lattice-based trick called lifting or dimensions for free, whereby instead of solving SVP or doing lattice sieving in the full lattice, you project down into a smaller lattice, solve SVP there, and then you project back up to your original lattice. This was done by Leo Ducar in 2018. Another thing you can do is work with the factor base itself. Instead of working with all primes up to B, you can consider all primes whereby you remove a couple or you remove a few. So you have this set P consisting of all primes up to B, but you remove some guesses. And this is some guessing that you have to do. There's no good way of making this guess. You just have to randomly guess which primes are not going to appear in the smooth twin. If you can combine these two things, and you can get this 213-bit smooth twin with a smoothest span of 1,000, which is the largest twin that we find in this work. Which is maybe a little bit annoying because I mentioned at the start that we would want to find these 256-bit smooth twins for cryptographic applications. But the computational cost of solving this SVP is really getting too much for these sort of examples, and we can't really go much further than this, which is kind of annoying, but it's just limitations of the SVP algorithms. And just to remark that this really isn't the optimal one. If you do the numerical approximations of that asymptotic result that I mentioned earlier, you can get an estimate of the optimal B-smooth twin to have about 227 bits, which is quite a bit larger than this. I also want to mention one final thing, which is on finding all B-smooth twins, because if you remember from the Pell equation approach, we can really find all of them and find them all quite nicely. And this was only done for B less than or equal to 113. And you might think, okay, can we do lattice sieving to enumerate all B-smooth twins and find every single one of them? And the answer is kind of no, because if you want to find all of them, you have to solve SVP in a whole bunch of lattices. You can't do it in one lattice, because sure, you'll find some short vectors that correspond to smooth twins, but there'll be other smooth twins that really aren't short anymore. And so you have to solve a whole bunch of short vectors. All of these short vectors you have to do in exponential time. So finding them all is kind of impractical, just from doing lattice sieving, let's say. But what you can do, and this is kind of a bit hopeful, is kind of combine two different approaches. Start with a large set that you've constructed somehow before, and then use this lattice sieving to see if you can find new twins that you didn't find before. And then from all of this computation, you might hope that you can get a complete set of B-smooth twins. And we did this sort of computation, and we only make a conjecture that we have the complete set of 200 smooth twins. And this is the precise number that we believe it should be. And precisely, we combined the CHM algorithm, which I hinted at before, whereby they found a very large set of 200 smooth twins, but not all of them, because we found 25 additional ones from our sieving approach. Once we found these 25, we don't stop there, because I have no idea if this is really the largest one. I really have to continue on for weeks and weeks to try and see if I can find some other ones. And after weeks of computation, I didn't find any. And it would be very surprising if there was another one, because it would, on the one hand, not be found in the CHM approach, but also correspond to a vector that's really, really not short. It would have to be incredibly large for it to be one to exist. No claims are made for larger B, but we could be close to having the complete set for the larger B. We have a public version of our code if you want to have fun with this. It's very accessible, and you can do all the things that I've talked about, all this guessing, solving SVP in the full lattice, lifting, blah, blah, blah. You can do this all here, which is quite nice. So let's wrap things up and summarize what we've done. We've discussed finding smooth twins, and in particular, we've found smooth twins from finding short vectors in a certain type of lattice called a prime number lattice, for which the basis is explicitly written like this. A very simple matrix basis to look at. From this, we were able to find much, much larger optimal twins compared to what we could do before. Before, we could only do this for b equals 113, and now we can do this for, let's say, b equals 751, which is really cool. And I mentioned at the start that we had some cryptographic applications, which I have not talked about at all. But there's some tricks that you can do to cover these primes for which you don't have everything being smooth, but you have some proportion of it being smooth. And you can do this from these smooth twins as well, with a small trick. With that, I think I'll wrap up there and see if there's any questions.
Thank you, Bruno. Are there any questions?
Thank you very much. I'm curious, you said it took a long time to get the b equals 1,000 example. How long did you have to run some kind of computing thing for?
A few days. So the runtime, it was a few days, and you could, in theory, do this for larger B and allow for a larger runtime, because you could, in theory, run this for weeks and find even larger ones. The trouble is, the big bottleneck is memory. You still have exponential memory to find these short vectors, just because you have to store lots of big lists of vectors. And going for larger B is, the memory is the big issue.
I'll ask a question. You said at the beginning that there's only a finite number of these smooth twins. What's the quick proof or intuition?
There's no quick proof or intuition that I can give.
Okay.
This goes all the way back to Stormer, and I did read this. I can't give a short proof. It's, yeah.
Okay.
Sorry.
Any other questions? All right, let's thank Bruno again.